first, I'm going to go ahead and steal some stuff from the add function. So I'm going to go ahead and grab public get, public set, and private get node. These should work exactly the same regardless of how long, of how big the node is, or how big the, how many pointers we have. Also, notice that when I copied it, it says, hey, do you want to use linkedlist.node? No. I'm going to cancel that so that it doesn't try to use linkedlist node class as opposed to our doubly linked list. Let's also cut and paste this guy down here. So we don't have to rewrite get set or get node. Similarly, there's no reason why we can't steal the toString, even though the arrow, and we'll just simply deal with the arrow like this. Cancel. Hey, look at that. So we can do the arrow like that. So we have stuff that we know works automatically. So that's quite nice already. So let's go ahead and write our add method. Public Boolean add e item. So this will add an item to the end of it. What did I call it? I still called it data. So public Boolean add e item. This dot add size and item, and return true. Might as well make ourselves a constructor before we forget. Public doubly linked list size equals 0. That's really all we need. And then let's see, add public Boolean add, or sorry, void add for this one. Void add int index e item. Okay, and finally, one last method to write. Public int size, which will, of course, return size, just exactly the same as the singly linked list. All right. So add, as I was saying, has 5 cases. The first, really, so we had the whole out of bounds case, but the main reason we had 2 other cases was if we modified what the head was, and if we modified what the tail. And so likewise, we'll have one for if we modify what the tail was. And finally, we have this last special case for the very first item that we add to a node, because that's a very special case. Or sorry, very first item we add to a linked list. That'll be a very special case where the resulting node is going to be both the head and the tail, because we're keeping track of both the head and the tail, right? If you have something of size 1, say this guy in his own linked list over here, right? His previous is nothing, his next is nothing. What is his status? He's both head and tail. He's going to be both of them. So we need something to reflect that. So here's our 5 cases. Out of bounds. And these are the 5 cases that doesn't matter that it's a doubly linked list or a singly linked list. If you're keeping track of a tail, you need these 5 cases. So out of bounds, adding very first node, or adding to empty list. Adding a new head. Adding a new tail. Adding, and then finally adding anywhere else. Likewise, for our remove method, it's going to be exactly the same 5 cases, only except over here, we would be removing the last item. So, great. So, public. So, sorry, now we want to do an if statement for our first case, if it's out of bounds. So, if index is less than 0, or index is greater than size, right? Greater than the last possible location we can edit, throw new index out of bounds exception. I'm not even going to bother filling it in at this point. Okay, so now adding to an empty list. How do I know if the list is empty? If the size is equal to 1 or 0, then we know that it's empty. Also, speaking of size, gotta remember to do that. Almost forgot. Size is equal, if the size is equal to 0, let's go and knock out our other conditions so we don't get too confused. Else if index is equal to 0, that's adding to a new head. Now, I'm making these mutually exclusive so I don't have to think about what's going to fall through to what, right? I don't have to think, okay, am I going to have multiple cases over here? This way I can, like, just isolate these scenarios individually. Else, if index, if we want to add to the last node in the list, then that would be an else if index equals the last possible location, which is size, and then else anywhere else, and then do size plus plus. Okay, so if the size is equal to 0, let's go ahead and make our node over here, because at this point we know we need the node. So node E adding is equal to new node that takes in the item. We'll need to write the constructor for that. Public node E item data, or data is equal to, yeah, I'm being bad and calling it data and item, but we add an item and nodes have data is the way I'm currently running it with this, so it should be fine. So let's see, if size equals 0, got our new node here. So if the size, so let's go ahead and see this case. If our case is this, we've just created a new node, and then what do we have to do? We need to make this guy the head and the tail. So head, this dot head is equal to adding, which will give it the adding label. And then we need to give it the tail label as well, because it's going to be both the head and the tail. This dot head is equal to adding. This dot tail is equal to adding. Okay. Case 3, if the index is equal to 0. Well, let's go ahead and check out what we've got over here. Move these guys over. Right, so we want to add this node to index 0 so that it can be the new head of the list. So how am I going to do? So what steps need to take place? So I need 2 more of these arrows guys. So Control C, Control V, Control V. So move these guys over here. So what I need to do is that the same rule still applies. I connect first and then I update the labels. So let's go ahead and connect this guy. So I want to connect this new node that I'm adding to the guy who's currently the head. So what I do there is I set my dot next to be the head. Similarly, what do I have to do over here? I have to, if I want to keep connecting it, I have to set heads dot previous equal to the tail. So I'm going to move this to the side for a second, and I'm just going to focus on, okay, how do I move this pointer to be here? That would be adding dot next is equal to head. Take the memory location of head and store it in adding dot next, so this means that this point's there. Next, I do head dot previous is equal to adding. Right? Because what I have to do now over here is connect head's previous pointer to go to here. What I don't have to fix is the new guy is adding's dot previous pointer, because that's going to go to null. That's perfectly fine. And heads dot next pointer, because we don't want to change that. So now I can just move this up here. Oh. And so we've got ourselves a new head, except we need to actually change the label to be this guy, so that when we start from the head, it's going to be this first node in the list. So head is equal to adding. So let's take a look at the difference between this and what we would get in the linked list for adding to the head. For adding to the head, adding.next is equal to head is equal to adding. So exactly the same, except we have one more line to have this pointer move over here. Okay. Now, if index is equal to size, let's go ahead and grab this guy over here and detach him. Right. So we'll detach him. We'll grab these fellas and move them this way because now we are going to move. We want to do a new tail. Okay, same things apply. We only need 2 new pointers right now. This will be the last one in this video, and I'll do the 5th case in its separate own video, just to break it up. Okay, so for adding, so if index is equal to size, then what do I want to do? I want to get the very last node in the list, which we're keeping track of. It's the tail. So the first thing we want to do is connect the new node and update it, and then update. So to connect the new node, what do I need to do? I need to first connect the previous's, or I need to connect adding to the tail, because I want to connect the node I'm adding first. So first thing I want to do is connect this arrow over here, which would be adding dot previous. Notice that is equal to tail, kind of the mirror image of what's going on for adding the first index. Then let's connect the tails pointer. Tail.next, which is currently null, is equal to adding, which takes this over here, right? And it will connect it to adding. Great. So this is pretty much the exact same, only like flipped around for the first index, or sorry, for the last index. So tail then is now equal to adding. So now that will take this label and store the memory location of the last node in it. And that's it for those cases. So in the next video, I'm going to go over the last case, which will just simply involve a lot of drawing.